Hey everyone, welcome back. So in this lesson, which is actually your last objective of this unit about probability, right? You've done a ton with probability. We're going to be learning about binomial probability. You have a lot of background knowledge about binomials. I feel like I'm actually giving away the lesson. I'm giving away the fun part of the lesson where well, I guess it's all still going to be fun, but I feel like I'm giving some things away by just telling you what we're learning about, binomial probability. So we're going to be able to calculate probabilities using binomial distributions, right? And so think about what we've already learned in general about binomials, right? And then you've done some work with the binomial theorem to expand binomials, right? Like if I have a plus b to the power of 10, you know exactly how you can use combinations to actually expand this, right? And so that's what we're going to be looking at today and how this all kind of ties together and plays in. So we're going to start off with this. An unfair coin is weighted in such a way that the probability of flipping a heads is 0.9. Pretty crazy coin. If we flip the coin 20 times, find the probability of flipping all heads, no heads, exactly 17 heads. So I would suggest maybe you pause the video right now and you try those. The first two, you know, right? Like the probability of flipping all heads, well, 0.9 times 0.9 times 0.9 times 0.9, right? Blah, blah, blah. Or realistically, I'm saying 0.9 to the power of 20, right? And whatever that might be. Do I know it off the top of my head? No, but I have it. This is about 0.122, right? There's a 12.2% chance of getting all heads. What about getting no heads, right? Or alternatively saying we're getting all tails of this extremely unfair coin. Well, I'm going to have 0.1 times 0.1 to 20 times, right? Times 0.1 and so on. I'm realistically getting 0.1 to the 20th power, right? There's virtually, or essentially no chance of that's going to happen, right? If you do that in your calculator. So it's a very minimal chance. So this one's a little different. If you tried it, I'd be curious what you came up with. What's the probability of getting exactly 17 heads? Well, if we relate it to what we just did in A and B, maybe you have something written on your papers that looks something like this, right? 0.9 to the power of 17 times 0.1 to the power of 3, right? You're flipping it 20 times still. 17 are heads, 3 are tails, right? And this is meaningful and this is important for us to recognize. I'm not going to make it go anywhere, but this is really the probability of getting 17 heads and then, I guess then 3 tails, right? Like in succession, like that would be the order that this is happening in, right? It's not, what about all the other ways that this could happen, right? Like think about like you've got it's like a word, right? I've got 20 letters, 17 of them are H, 3 of them are T, right? 17 heads, 3 tails. How many different ways can I order that? This is limiting it a little bit because this is just one possible way to get it, right? I could get 17 heads and then 3 tails, right? 17 H's and then 3 T's. But what if those T's are scattered? What if things are moved around a little bit? Well, what can I do to figure that piece of it out? Oh, well, how many ways are there to arrange those letters? 20, choose 17. Or alternatively, I could have said 20, choose 3, right? That would have been fine too. 20, choose 3, 0.9 to the 17th power, 0.1 to the 3rd, right? That's accounting for all of those other ones. So, or you can even think about it with when we were ordering words, letters in words, And you would say, well, there's 20 factorial divided by the repeats, right? 17 factorial, 3 factorial, 17 H's, 3 T's, that you're not, but if I flip 2 of the H's or I switch 2 of the H's, it looks the same to us. It's not, one's not more meaningful than the other, which is just 20 choose 17 or 20 choose 3, they're the same. Okay. This is approximately, if you did this in your calculator, approximately 0.19. Ooh, that's an interesting square. It's not a square. So what if I asked you this? 17 or more, right? So 17 or 18 or 19 or 20, right? This was exactly 17. Well, let's keep going with that, right? 20 choose 17. 0.9 to the 17th, 0.1 to the 3rd, plus 20 choose 18. 0.9 to the, what am I doing? I'm going up 18. 0.1 squared, plus 20 choose 19. 0.9 to the 19. 0.1 to the first, right? And I could do this last one, or realistically, it's just what we did up here, right? Because 20 choose 20 is just 1. And then 0.9 to the 20th power, 0.1 to the 0 if I want to keep going, right? And this is approximately, when you do all this nice math in your calculator, you're going to get approximately 0.876, right? This should look familiar, and especially because I said, and it's written up here, that I was giving away what we were doing. This should remind you, ideally, of the binomial theorem, right? Or binomial expansion. Right? That this is really of that format when we would have, if I was doing a plus b to the power of 20, and I would write them all out, and you would have 20 choose 0, a to the 20th, b to the 0, plus, right? Like that's really what ideally this is reminding you of. So what we're looking at here is a probability distribution. Right? So suppose an event consists of n independent trials, right? In that problem before, we were doing 20 triangles with 2 outcomes, success and failure, right? There's not, I think, don't get caught up in the word success and failure. It's just there's 2 outcomes that are possible, right? Like getting a heads, getting a tails. Where probabilities P and Q, where Q is 1 minus P. Right? It's the complement is something that we talked about. Right? That's the complement of it. Then the terms in the expansion, P plus Q to the power of n, give the probabilities of exactly n minus 1, right? However many trials there are. So you could get up to n successes, or you get n minus 1 success, n minus 2, right? That's the expansion. That's the binomial expansion that's happening. The other thing I do want you to take a look at is, what is this really equivalent to? Right? P plus Q is just 1. Does that make sense? Right? That's why it's a distribution. All of these probabilities should add to 1. Right? Like if I take all of the possible outcomes that could happen of success and failure and I add them all up, I should get 1. Like arguably that should make sense. Right? So looking at something that's really similar to what we just did in the last problem, now that we've kind of seen this, Alex makes 80% of his free throws. If he shoots 20 free throws, what is the probability that he makes all 20? Well, in the last problem, we just said 0.8 to the power of 20 would be our answer to this, right? But realistically, it's 20 choose 20, right? It's one of the expansions. It's just the first one, right? 20 choose 20, 0.8 to the power of 20. This is just one. That's all that's happening there, right? And if you go ahead and do this in your calculator, you're going to get about 0.115, I believe. What's the probability of getting exactly 18? Well, this is also just, I'm picking one of those values. 20 choose 18, 0.8 to the power of 18, right? So this is the ways that you can arrange those 18 successes. right? With those 2 failures, those 18 that are made, the 2 that are missed, right? And I get approximately 0.137. Well, what about at least 18, right? So there might be 18, there might be 19, 20. You could get all 20, right? And so we want to take what we've just done, what's the probability of getting 18 plus the probability of getting 19 plus the probability of getting 20, right? It's part of the expansion. Sorry, got ahead of myself before I wrote the answer, which is approximately 0.206. So if we take a look at this example here, in a factory that produces widgets, 0.8% of the widgets are defective, right? And so this is really where technically, like, getting a defective widget, like, yay, that's a success. That's why I was like, don't worry too much about the word success versus failure. So 0.8% of the widgets are defective. What is the probability that 3 widgets are defective if we pull 150 off of the production line? Right? So let's think about this. So N is the number of trials, right? So that's where we're getting, sorry, I got ahead of myself, 150. P is the probability of a success, of pulling a defective widget off of the production line, right? 0.8%, so what is that? 0.008. Q is 1 minus P, it's the complement, right? So that's where we're gonna get I certainly have something, I wrote it down weirdly in my, it's 0.992. Did subtraction incorrectly on my paper. And then X, right, is saying like, well, what are we looking for? 3. Right, so X is going to be 3. So we can go ahead and, just like we know this binomial expansion, well, I know which term I'm specifically looking for, right? So I now have this. I can go ahead and say, well, it's 150, choose 3, right? I'm picking that specific term that I'm looking for here, 0.008 to the power of 3, and then 0.992 to the power of, what is this? 150 minus 3, so 147. And we know how to do this in our calculators, right? So I can go ahead and say 150, choose 3, and then times 0.008 to the third, times 0.992 to the 147. And I get approximately 0.0867. Yeah. Right, so that's the probability of picking 3 defective widgets out of 150. So we can also link this in with what we talked about in our last lesson, right, when we saw you guys last. So the expected value and the variance of a binomial random variable. So the expected value and variance of a binomial random variable x with parameters n and p can be written this way. This, I mean, there's a little bit more math that would need to go into this. I could also say what? N times P times Q, right? That's the same thing. Expected value, I think, makes some sense, right? If I pick 150 off of the production line, how many do I expect to get, right? And so we can actually figure that piece of it out. And so let's go ahead and do that. So if I picked 150, the expected value of that occurring out of 150 times the probability of getting 1, right, I get, let's see, 1.2, right? And that's a little That's a little silly. Like, it's literally not possible to get 1.2. But what this is indicating is that on average, like if we did this day in and day out and we picked 150, like you would expect on average to get 1.2 for every 150, right? You're not actually going to get 1.2. It's the expected value. The variance is 150 times, right, 0.008 times 0.992. Was that what it was? So 150 times 0.008 times 0.992 is 1.1904, right? Which is the spread of it. It's a measure of spread, which related to standard deviation, which you talked about last time. So how about this? And this is a really similar concept to what we've just done in the last few examples, right? So a survey shows that 6% of American drivers text while driving. That's awful. If 300 US drivers are selected at random, find the probability that exactly 25 say they text and drive. And they're telling the truth, hopefully. Well, yeah. Oh, sorry. Right, so here what's happening is, well, out of 300, I'm picking 25, so just like we just did, 6%, so 0.06, say they do text and drive, so the 25th power, times Q, or 1 minus that, so that's going to be 0.94 to however many else there are, 275. And in your calculator, when you go ahead and do this, hopefully you're getting this value. What about this? What about if it's at least 25, so 25 or more, right? So you guys aren't afraid of this. You can totally do this, right? So 300, choose 25, 0.06 to the 25th power, 0.94 to the 275th, plus, okay, let's keep going, 300 to the 26, choose 26, 0.06 to the 26, times 0.94 to the 274th, right? And you just keep going. There'll only be one of these on the test. Just one. It can take a little bit of time, so you'll only have one where you have to go all the way up from 25 to 300 about. Right? You totally can do that. I don't know. It might be a pain, right? But you have an alternative, right? I could make it a little bit easier. We could do the other side, right? Instead of doing at least 25, let's do we know that it adds to 1, right? It's a probability distribution. I know that it's going to add to 1 when I add all of these up. So I can just do the other side. I can do 1 minus 24 or less, right? That's not as bad. I can figure out all of those, and I could do 300 choose 0, 300 choose 1, 300 choose 2, and just go up to 24, right? That's probably less work. I don't know. It still doesn't sound like terribly much fun. So let's go ahead and let's look at how we can do this in our calculator. And we'll talk about, those of you in stat may already probably know where this is going. But let's talk about how we can do it with exactly 25. Like, I don't even know if I want to call it a shortcut, but a shortcut to do exactly 25, right? And so there's a function in your calculator, and I'll show this in a moment, binomial PDF, right? Probability distribution function. And if we go to second vars, we will see it in there. And what we're going to be doing is we're literally going to enter these values of n, right? These parameters. So n is, what was n? 300. P is the probability of a success, picking somebody who does say they text and drive. Interesting success. 0.06. And then X is how many we're looking for. So that's 25, right? And that's the exact value. Like, I'm trying to find that exact one. So I'm going to keep this, then you're going to see the rest of it. So this isn't going to be so fun. And I'm going to go and open my calculator. Can I do it? No, I can't do it. Okay. I just downloaded this calculator, so we're going to see how it goes. Second vars, right? That's distribution. And I can see binomial PDF. So I'm going to push enter. And I'm going to enter these. 300, comma, 0.06, comma, 25. And let's see. Oh, goodness. Oh, no. I literally clicked the wrong button. You guys didn't tell me that. Second vars. Oh, it's all the way down here. Sorry. New oh, goodness. There it is. I was like, something doesn't make sense. Oh, it looks different on this calculator. Okay. So number of trials. Oh, this like gives it away. 300. P, the probability of success is 0.06. The X value is 25. Oh. And oh, wow, that's what we got. I don't know that that's necessarily that much of a shortcut, but it does something, right? So if you're going to pretend that the rest of this stuff isn't down here, maybe. Can you do that? Can I cover? You guys, I can already see it. So now this is less going well for me, but that's okay. So I'm going to go ahead. I'll zoom in a little bit. So when we do this at least 25, well, my calculator can help me out with that too. It has this other function, binomial CDF, right? And what this calculates is it calculates an amount and less, right? This is a specific value. Binomial PDF is just one value. Binomial CDF is that number and lower, right? And so we kind of got at this with 1 minus 24 or less, because we know they all add up to 100 or 1, 100% or 1. And so we can go ahead, and I'm not gonna do it with 25 because I want it to be at least 25. Whoa, that's a large pen. So we want to go ahead and we want to do something like 1 minus binomial CDF, 300, same values, 0.06, but then not 25, we want 24, right? Because I want 25 to be included in that at least. And so let's go ahead here. And so instead of you're welcome to sit there and add them all up and see if this is correct. Sounds like a fun afternoon activity. So second vars. Can this thing go away? I don't want it to tell me more. I want it to just literally go away. No! Binomial CDF. Oh my gosh. Okay. This isn't going so well for me, guys. Second vars. You're probably already done if you're still there. $300. 0.06. And then what was this? 24 in this case. Right? Maybe I even want to go back over here. This is going well. And insert. It's stuck on the going back button. Okay, just enter. This is painful. There you go. And then I'll go ahead and do 1 minus that instead. I could have just done that before. Oh my gosh, I didn't even click binomial CDF. Wow, I'm frustrating myself now. Second, no. 1 minus second vars, enter. Okay, I've got all of that information. There you go, enter. There you go. Finally got it. Hopefully I got it correct, right? So 0.0622, 0.062, right, is what this ends up being, approximately. Right, and so we want to remember that this here, binomial PDF, is calculating just one value, whereas this is calculating that amount and less, right? So 1 minus up to 24. So it's the probability that x is greater than or equal to 25 is 1 minus the probability that x is less than or equal to 24. Okay? So it's calculating the left tail. Is an important thing to recognize. Let's finish up with this last example, which I'm not convinced I'm going to pull the calculator back out on. So, of the members of a bowling league, this sounds really exciting, 10% have their own bowling shoes. If 200 bowling league members are selected at random, okay, so that's how many trials, find the probability that more than 10 have their own bowling shoes. Okay, let's start with that first part. I'll call that A. So let's think through this. So I have N is, what was that? 200. The probability of a success, P, is 10%, so 0.10. And then X is saying more than 10. I mean, maybe I'm thinking about 10, more than 10. So 10 is not included in that, right? So realistically, what I'm finding here is the probability that X is greater than 10, which is the same thing as 1 minus the probability that X is less than or equal to 10. So let's think through that and indicate that piece of information. So in my calculator, I want to go ahead and think about this and say 1 minus binomial CDF, right? You're not just finding 1, you're finding that and less, right? For this right here, 200.10, 10. In my calculator, I'm going to do it on my handheld calculator. 1 minus binomial CDF is 200.110. I get approximately 0.992. Okay, so that's the probability that more than 10 have their own bowling shoes. Let's look at this second part. Also, find the expected number of members who have their own shoes and the standard deviation, right? So this formula was back there a little bit, right? So expected value was the one that I said makes some sense, right? If you think about it logically. So the expected value is N times P, which is going to be 200 times 0.1, which is 20, right? So the expected number would be 20 people. And the variance, remember that was, we're doing NP, I should have written that first, NPQ, right? 0.1 times Q would be, well, the complement of this, so 0.9. So 200 times 0.1 times 0.9, I get 18 would be the variance, right? And so if I'm going to find the standard deviation, the variance is the square of the standard deviation. the standard deviation is going to be the square root of 18. Okay, or approximately, I did that wrong. Approximately 4.243. Okay. So, oh, of course, watch out. There you go. So in this lesson, you guys saw me struggle with the calculator, but that's okay. It happens. So we went through and hopefully you saw a lot of interesting connections between some of the things that we've done and you've learned, and there's a lot that you can do with probability and interesting probabilities you can find. But our focus is on the binomial probability and using what we know about binomial expansions to actually find some probabilities. So make sure you guys are practicing and using your resources, and we will see you all soon in class. Thanks, everyone. Oh, goodness.